This is a video for AQA Further Pure, complex numbers 6 exponential form, 6.5 summing series using de Moivre's theorem. Before we start, we should just check that you have already come across some things that we're going to use. You should know about geometric series and how to find the sum to n terms using this formula. And you should know about the sum to infinity using this formula, and that you need to have that r is less than 1 for that to be valid. You should also know about binomial coefficients using either NCR or the vector NR to represent that binomial coefficient, and using this formula for the calculation. Finally, you should know how to multiply out binomial expansions of the form a plus b to the n. So let's have a look at summing series that involve complex numbers. In this first one, I've got a first term a and a common ratio, which is z, and z is a complex number. And this will give me that the sum to n terms is going to be a times 1 minus z to the n all over 1 minus z. And I can form an expression for the sum to infinity, which is a over 1 minus z. And that's provided that mod z is less than 1. A slightly more specific series here with a equals 1 and r equals e to the I theta gives me this. So the sum to n terms for this is going to be 1 minus e to the I theta to the power n all over 1 minus e to the I theta. And this will simplify to 1 minus e to the I n theta over 1 minus e to the I theta. Now in fact the modulus of e to the I theta is equal to 1, so sum to infinity is undefined. There's that written out so that you can see it a little more easily. There's my expression for the sum to n terms and the sum to infinity, provided that the mod z is less than 1. And this is very much what we would expect to get from real numbers, and it works in just the same way for complex numbers. And so, considering the more specific series, there's the series written out in a new form for you. And you'll see here this will involve cos and sine of theta, this will involve cos and sine of 2 theta, cos and sine of 3 theta, and so on. So that actually will be very useful if we're looking at multiple angles. And here, that's just written up that sum to n terms again. Saw that on the last slide, and just confirming that we don't have a sum to infinity because the modulus of the common ratio is equal to 1. So now in this example we've got an expression here, and we want to find out what that is and then use it to simplify the sum of this series. Notice that this series involves sines of multiple angles. So that special series with e to the I theta I think is going to be useful here. Let's start with the two brackets though. Let's see what happens with those. So there's my two brackets. And what happens if I multiply them out? Well, I'm going to get 4 plus 2e to the I theta plus 2e to the minus I theta plus 1. And if I just tidy that a little bit, I'm going to get that that's 5 plus 2 lots of e to the I theta plus e to the minus I theta. Now, in a previous video we've seen that this is just 2 cos theta, and so I can straight away rewrite this as 5 plus 4 cos theta. Now let's have another look at this series here. So sine theta over 2 minus sine 2 theta over 4 plus sine 3 theta over 8, etc. We talked about that special series on the last slide. Might involve multiple angles, and I think that this has come from a GP where the first term is 1 and the common ratio, rather than just being e to the I theta, I think it's going to be an e to the I theta over 2 type thing, hence we'll get these 2, 4, 8 and so on as we power up. And I think it's going to need to be negative because I've got a change of sign here, so things are happening on alternate powers. So let's have a look at how this series works out. First thing I'm going to do is I'm going to write it as C plus IS is equal to, I'm splitting the series into 2 bits, the real and imaginary bits, and as it turns out, as you'll see, C will be all of the cos type bits and S will be all of the sine type bits. So if we write out the series, then it's going to be 1 plus minus e to the I theta over 2 plus minus e to the I theta over 2 squared plus minus e to the I theta over 2 cubed, and so on. And that gives me 1 minus e to the I theta over 2 plus e to the I 2 theta over 4 minus e to the I 3 theta over 8, etc. And so now, expanding the e to the I theta things, we're going to get that C plus IS is equal to 1 minus e to the I theta is going to give me cos theta over 2 minus I sine theta over 2. The next bit is going to give me plus cos 2 theta over 4 and plus I sine 2 theta over 4, and then cos 3 theta over 8 minus I sine 3 theta over 8 plus whatever else comes along. And so now if I look at the real and imaginary parts, C is going to give me 1 minus cos theta over 2 plus cos 2 theta over 4 minus cos 3 theta over 8, and so on. And S is going to be minus sine theta over 2 plus sine 2 theta over 4 minus sine 3 theta over 8 plus the rest. And so the sum that we're after, that's this thing up here, looks very like the imaginary bit of that series. And we actually want minus S, and S is equal to the imaginary part of the sum to infinity, because remember this is an infinite series. There's that written up again so you can follow it. Notice here we've just used the expansion of e to the I theta and e to the minus I theta rather than the fact that this is equal to 2 cos theta. Exactly the same result, you get the same answer. Here's looking at this series and establishing that we think it might have come from there, and indeed working that through, calling the series C plus IS, we get expressions for C and S, and the fact that we want minus S, where S is the imaginary part of the sum to infinity for this series. So moving on from there then, This is where we'd got to. We'd established this result, and we want minus s, where s is the imaginary part of the sum to infinity for this thing here. So let's look at s to infinity. Well, the first thing we need to check is whether or not it exists. And if we look at the modulus of r, that's going to be the modulus of minus e to the I theta over 2, which is just equal to a half. Now that's less than 1, so we're happy that the sum to infinity exists. So if we now look at the sum to infinity, the sum to infinity is going to be a over 1 minus r, so that's going to be 1 over 1 plus e to the I theta over 2. If I just tidy that a touch, I'm going to get 2 over 2 plus e to the I theta. And this thing here is the same as this that we were asked to work with on the first question. So what I'm going to do is I'm going to put in a factor of 2 plus e to the minus I theta, and I'm going to put that in top and bottom. So it has no overall effect. Now on the bottom here now, I've got 2 plus e to the I theta times 2 plus e to the minus I theta, and I know that I can replace that with 5 plus 4 cos theta. So if I sort out the top line, I'm going to get 4 plus 2e to the minus I theta all over 5 plus 4 cos theta. And that, just tidying up what this means, that's going to be 4 plus 2 cos theta minus 2i sine theta, and that's all over 5 plus 4 cos theta. Now the nice thing about that expression is I can split out the real part of that and the imaginary part of that with ease, and I want the imaginary part, remember, of this sum to infinity. So we know that s must be equal to the imaginary part of the sum to infinity. So I'm going to get that my minus sine theta over 2 plus sine 2 theta over 4 minus sine 3 theta over 8, etc., is equal to the imaginary part of this, which is just going to be minus 2 sine theta over 5 plus 4 cos theta. And the series I actually wanted is a sine flip on this. So it's sine theta over 2 minus sine 2 theta over 4 plus sine 3 theta over 8 minus the other bits. And so I'm going to get a sine flip here. So that's going to be 2 sine theta over 5 plus 4 cos theta. There it is, written up more tidily again, just establishing that there will be a sum to infinity because the modulus of the common ratio is less than 1. And then working this through, and there's that trick to establish the thing that we were given in the first part of the question. Again, it's very common to use the first part of the question in solving the second, and that you should always go looking for that. And there's my expression for the sum to infinity. And then this is just equating what is effectively minus s with the minus part of the imaginary part of the sum to infinity. So in summary, we can look at complex series in more than one way, and what we were doing then was looking at the series itself and how its sum to infinity or sum to n terms might work out. Looking at the real and imaginary parts separately can provide useful results which don't actually contain any complex numbers, and that's exactly what we did with that last series. We often use this type of expression, C plus IS, where C is the real part and S is the imaginary part of a series, and the C part often ends up involving causes of multiple angles and the S sines of multiple angles. C plus IS may actually be given to you in the context of the question, and it often comes from a series involving e to the I theta. That was the final video in this sequence, complex number 6, exponential form.